Hello students, I hope you all are doing good. Today we are going to discuss NCERT section 10.3 to 10.3.3 of chapter Wave Optics. This is the disclaimer. In today's lecture, we will be focusing on understanding some fundamental principles of wave behavior in physics. By the end of this session, you will have the ability to derive and explain key laws that govern how waves interact with different media. Let's start by looking at what you will be able to achieve after this lecture. So first you will be able to understand and derive Snell's law of refraction. This law helps us understand how waves change direction when they pass from one medium to another. Using Huygens principle, we will explore how waves behave differently in denser versus rarer medium. Next, you will be able to derive the law of reflection using Huygens principle. This will help us understand how light behaves when it encounters surface like prisms, lenses, and mirrors. We will use wave theory to explain these interactions, highlighting the predictable nature of wave behavior in various optical devices. So today we are going to explore the fascinating concepts of refraction and reflection of plane waves using Huygens principle. This principle helps us understand how waves propagate through different media. Okay, next we will discuss NCERT section 10.3.1, which is about the refraction of plane wave. Refraction occurs when a wave passes from one medium to another, changing its speed and direction. This is crucial for understanding phenomena like lenses and prisms. Imagine a straw in glass of water appearing bent. That's refraction in action. So next we will focus on NCERT section 10.3.2, which is refraction at a rarer medium. When a wave moves from denser to a rarer medium, it speeds up and bends away from the normal. This concept is important for technologies like fiber optics, where light travels through different media efficiently. Finally, we will examine the reflection of plane wave by a plane surface. Reflection occurs when a wave bounces back into the original medium. Think of how a mirror reflects light, allowing us to see our reflection, which is NCERT section 10.3.3. So we are going to recall the Huygens principle, a fundamental concept in wave theory. Our objective is to understand how this principle explains the behavior of waves. Let's start by defining what the Huygens principle is. So Huygens principle states that every point on a wavefront acts as a source of secondary wavelets. Okay, so these secondary wavelets spread out in all the directions. So every point on a wavefront acts as a source of secondary wavelets. Okay, imagine some points on the given wavefront or primary wavefront. Okay, so secondary wavelets, these points will act as a source of secondary wavelets. Okay, so these wavelets spread out in all the directions with the same speed as the wave. Okay, so the new wavefront formed as the envelope or tangent surface of all the secondary wavelets. Okay, so point source. So from every point of a primary wavefront, these point acts as a secondary wavelet. And secondary wavelets are also in the form of spheres because they are generating from a point on a primary wavefront. Okay, so these wavelets spread out in all the directions with the same speed as the wave. So the new wavefront is the envelope, or we can say tangent surface of all these secondary wavelets. Okay, so tangent, a surface drawn touching all the secondary wavelets after time t, will give the new wavefront at that time t. Okay, it is the tangent surface of all the secondary wavelets at some instant. So phenomena of refraction and reflection can be understood using Huygens principle. So we can explain the reflection. When a wavefront hits the reflecting surface, each point generates secondary wavelets that combine to form the reflected wavefront. Also, in the same way, we can explain the phenomena of refraction. Okay, so using this principle, you can explain reflection. When a wavefront hits a reflecting surface, each point on wavefront generates secondary wavelets that combine to form the reflected wavefront. Okay, we will see in detail in this lecture. And refraction, when light passes from one medium to another, the change in wave speed. Okay, speed of the wave changes when it goes from one medium to another medium. When it goes in denser medium, its speed decreases. When it goes in rarer medium, its speeds increases. Okay, so the change in wave speed results in change in direction. So the secondary wavelet travel at different speeds in different media, explaining why light bends at interfaces between the materials. Okay, so these wavelets also travel at different speed in the different media. That's why, by the help of wave theory or by the help of Huygens principle, we will explain why light bends at the interface between the materials. Okay. Now our objective is to find the refracted wave in denser medium. Notice the diagram showing a plane wave AB incident on the surface. You can see in the diagram a plane wavefront AB is incident on the surface on P dash. That is the interface. Okay, separating two media. This setup will help us understand how the wavefront changes direction as it encounters a denser medium. You can see the refracted wavefront, that is EC. It is not parallel to AB. Okay, so it is changing direction after refraction. So in the diagram, there is medium 1, medium 2. And wavefront is going from, or wave is going from, or light is going from rarer medium to denser medium. Okay, why medium 2 is denser? Because it is given that V1 is greater than V2. So in medium 1, speed is more. That means medium 1 is rarer, or that is AB is incident wavefront. Okay, A dash A is incident light ray. Okay, light ray is always perpendicular to wavefront. Okay, P dash is interface. Got it? So figure 10.4, a plane wave AB is incident at an angle I. Okay, it is incident at angle I on the surface P dash separating medium 1 and medium 2. The plane wave undergoes refraction and CE represents the refracted wavefront. The figure corresponds to V2 less than V1. Means speed in the second medium is less than that of first medium, so that the refracted wave bends towards the normal. Okay, so let's focus on surface P dash in the diagram. This surface acts as a boundary between medium 1 and medium 2. It's important to note that this boundary is where the refraction occurs, causing the wave to bend. Keep in mind that properties of these two media will affect how the wavefront behaves. Now consider the speeds of light in these two media represented by V1 and V2. In medium 1, light travels at speed V1, while in medium 2, it travels at speed V2. The difference in speed is crucial because it determines how much the wave will bend. Okay, remember when light enters a denser medium, its speed decreases, which is why V2 is less than the V1 in this scenario. So let's examine the wavefront AB, which is moving in the direction A dash A. Okay, that is its direction of motion. As it hits the interface at an angle I, it undergoes refraction. This angle of incidence is key to understanding how the wavefront will change the direction. Notice how the refracted wavefront CE bend towards the normal. Okay, illustrating the principle that light slows down and bend towards the normal when entering a denser medium, as shown in the figure 10.4. So we are going to explore how to find a refracted wave using Huygens principle, specifically when dealing with a denser medium. Took a look at figure 10.4, which help us visualize the process. Notice how the wavefront interacts with the boundary between two media. So let's start by considering the time it takes for a wavelet to travel from point B to point C. Okay, we will denote this time as tau. This is crucial because it sets the stage for understanding how the wavefront progresses. In this step, we define the distance BC as v1 times tau. Why? Distance traveled is given as speed into time. So speed of this wavefront is v1 in medium 1. And what is the time taken to secondary wavelets to go from B to C is tau, where v1 is the speed of wave in the initial medium. This equation helps us quantify the waves travel in the first medium. Now after the wave enters the new medium, its speed changes to v2. This change in speed is important because it affects how the wavefront bends or refracts as it moves into the denser medium. So during the same time tau, the wavelet from point A travels a distance AE, which is v2 times the tau. Okay, after time t, secondary wavelets from B travel from B to C. For the same time, secondary wavelet from A travels to E point with the speed v2 into the second medium. This shows us how the wavefront continues to propagate but at a different speed. Finally, let's introduce the angle of refraction denoted as R. This angle is key to understanding how the wavefront changes direction as it enters the new medium. So let's start by understanding how the wave bends at the interface between two media. Our first step is to identify a point on the interface. This will help us track the wave's path as it enters the second medium. So now focus on point A on the interface as shown in the diagram. By selecting point A, we can begin to visualize how the wavefront will change. So next we draw a sphere with the radius equals to v2 times t from point A in the second medium. This sphere represents the wavefront potential reach over time. Okay, so it represents the wavefront ability to reach over time. Okay, for how much distance secondary wavelet will travel or wavefront will travel in time tau in the second medium. Okay, so remember v2 is the speed of light in the second medium and tau is the time. Now let's introduce the tangent plane representing CE, drawn from point C to the sphere. Okay, draw tangent from C to point to that sphere, or we can say to that circular arc we drawn. Okay, that sphere in 3D. So this tangent plane is key because it shows us the direction of refracted wavefront. It's like drawing a line that touches the sphere without cutting through it. Finally, we see AE equals to V2 times tau and CE represents refracted wavefront. Okay, so this tells us how the wavefront bends as it enters the denser medium. The refracted wavefront is crucial for understanding how light behaves in different materials. So we are going to explore the derivation of Snell's law using Huygens principle. Okay, so our objective is to understand how light behaves when it passes from one medium to another. So in triangle ABC, we can express the sine of angle I as the ratio of opposite side BC to the hypotenuse AC. This gives us the equation sine I equals to BC upon AC equals to V1 multiplied tau upon AC. Here V1 represents the speed of light in the first medium and tau is the time taken. Mark it as 10.1 equation. Now let's examine triangle AEC. This is where the light ray enters the second medium. In triangle AEC, the sign of angle R is given by the ratio AE upon AC, which equals to V2 multiplied tau upon AC. Mark it as 10.2 equation. Here V2 is the speed of light in the second medium. By comparing these two equations, we will be able to derive Snell's law. So here our objective is to understand how light behaves when it passes from one medium to another. So let's start by looking at the equations for the sine of the angle of incidence and sine of the angle of refraction. We have sine I equals to BC upon AC equals to V1 multiplied by tau upon AC, and sine R equals to AE upon AC, which is equal to V2 multiplied by tau upon AC. Here I is the angle of incidence, R is the angle of refraction, V1 and V2 are the velocities of light in the respective media, and tau is the time taken. So next we will divide these two equations to simplify our understanding. This step is important because it allows us to relate the angles of incidence and refraction directly to the velocity of light in the two media. So by dividing the equations, we get sine I upon sine R equals to V1 multiplied tau upon AC multiplied by, divided by V2 multiplied tau upon AC. Okay, so notice how tau and AC terms, so AC and AC terms, denominator of both these terms will cancel out. AC and AC will cancel out. Okay, so simplify our equation. This shows the relationship between the angles and the velocities of light. And AC term will cancel out. Also tau term will also cancel out. Okay, so finally we arrive at the equation sine I upon sine R equals to V1 upon V2. This is Snell's law, which tells us that the ratio of the sines of angles of incidence and refraction is equal to the ratio of the velocities of light in the two media. So let's reveal the mathematical expression for Snell's law. This equation is sine I upon sine R equals to V1 upon V2. Here I is the angle of incidence, R is the angle of refraction, V1 is the speed of light in first medium, and V2 is the speed of light in the second medium. So now let's move on to the conclusion. We will discuss what happens when angle of refraction is less than the angle of incidence. This means the light ray bends towards the normal, indicating that speed of light in the second medium is less than in the first medium. So according to corpuscular model, light should speed up in the second medium, but our findings show otherwise. Okay, so if R is less than I, means angle of refraction is less than I, if the ray bend towards the normal, the speed of light wave in the second medium will be less than the speed of light wave in the first medium, that is V1. So experiments have confirmed that wave theory's prediction is correct. This reinforces the validity of wave model of light over the corpuscular model. It's important to understand how experimental evidence support the theoretical predictions. Okay, so experiments have showed that prediction of the wave theory is correct. So our objective is to understand how light behaves when it passes from one medium to another. So let's start by recalling the definition of refractive index. The refractive index is a measure of how much the speed of light is reduced inside a medium compared to the speed of light in the vacuum. So here we have the equation for the refractive index of first medium. So N1 equals to C upon V1, which is equation 10.4. In this equation, C represents the speed of light in a vacuum, V1 is the speed of light in first medium, and N1 is the refractive index of first medium. So similarly, for the second medium, we have N2 equals to C upon V2. C is the speed of light, V2 is the speed of light in the second medium. C is the speed of light in vacuum. By comparing these two equations, 10.4 and 10.5, we can start to see how the refractive indices of different media are related. So now let's divide the equation for N2 by equation for N1. Notice how this division will help us derive a relationship between the speeds of light in the two media. So the result of the division gives us N2 upon N1 equals to V1 upon V2. This equation shows the relationship between the refractive indices and the speeds of light in the two media. So let's start with the relationship between the refractive indices and the velocities of light in two media. We have the equation N2 upon N1 equals to V1 upon V2. Here N1 and N2 are the refractive indices of the first and second medium respectively, and V1 and V2 are the velocities of light in these media. Notice how the refractive index is inversely proportional to velocity of light in the medium. Okay, so more is the velocity, less is the refractive index. From equation 10.3, we know that sin I upon sin R equals to V1 upon V2. This equation relates the angle of incidence I and refraction to the velocities of light in the two media. It's important to see how the angles and velocities are interconnected, which will help us understand the bending of light. Now substituting the velocity ratio with the refractive index ratio, we get sin I upon sin R equal to N2 upon N1. This step is crucial because it connects the angle of incidence and refraction directly to the refractive indices, which are easier to measure and use in practical applications. This leads us to the equation N1 multiplied by sin I equal to N2 multiplied by sin R. This is the key step in our derivation, showing that the product of refractive index and sine of the angle is constant across the boundary. This equation is fundamental in understanding how light refracts at the interface of two media. Okay, so this is Snell's law of refraction. Okay, this law is essential in optics, explaining how light bends when it passes from one medium to another. So we are going to explore what happens when a wave is refracted into a denser medium. Our objective is to understand the changes that occur during this process. So now we introduce the concept of wavelengths in different media. Let lambda 1 and lambda 2 represent the wavelengths of light in medium 1 and medium 2 respectively. Notice how we use these symbols to differentiate between the two environments. So now let's delve deeper. If the distance BC is equal to lambda 1, okay, then lambda 1 equals to V1 times tau. Okay, so this equation shows the relationship between the wavelength, velocity and time in the first medium. Take a look at figure 10.4 to visualize this concept. So next we introduce another variable AE, which we denote as D. Here D equals to V2 times tau. This equation is similar to the previous one but applies to the second medium. Now we see the equation D equals to V2 times lambda 1 divided by V1, because lambda 1 is equal to V1 tau. So we can write V1 tau is equal to lambda 1. Okay. So D is equal to V2 tau. So tau we have written as lambda 1 upon V1. So this equation helps us understand how the distance D is related to the velocities and wavelength in two media. So finally we have the equation D equals C divided by N2 multiplied by N divided by C multiplied by lambda 1. Here we use the relationship V equals C upon N. Okay, so we have written V1 equal to C upon N1 and V2 equal to C upon N2. Got it? Here we use the relationship V equals to C upon N, where C is the speed of light and N is the refractive index. This equation ties together the concept of speed, refractive index and wavelength. So notice the formula V equals to C upon N, where V is the speed of light. V is the wave speed, C is the speed of light in vacuum, and N is the refractive index. This equation helps us understand how the speed of a wave changes with the medium. Here we see the equation D equals to lambda 1 upon N21, where D represents the distance, lambda 1 is the wavelength in the initial medium, and N21 is the relative refractive index of second medium with respect to first medium. Okay. So N21 is equal to N2 upon N1. This equation shows us how wavelength changes when moving into a denser medium. Okay, so let's look at relationship between wavelengths in different media. The equation lambda 2 equals to lambda 1 upon N21 tells us that wavelength in the second medium, lambda 2 is shorter than the first medium due to refractive index. Okay, so wavelength in another medium is given by, so since lambda 2 is the wavelength in the second medium, is given by lambda 1, that is wavelength in the first medium, upon N21, that is the refractive index of second medium upon with respect to first medium. Okay, so this is a formula for finding the wavelength in the another medium or in the second medium. Okay, so distance A is equal to lambda 2, or we can say distance D is equal to, we assumed A equal to D, so D is equal to lambda 2 here, because this expression resembles lambda 2 equal to lambda 1 upon N21. Okay, so that's why D is equal to lambda 2. So finally we see that distance A equals to lambda 2. This reinforces the idea that wavelength in the denser medium is shorter. As we conclude, remember that the change in wavelength is a key factor in the refraction process. Okay, so wavelength, when light goes from one medium to another, so wavelength changes by, so wavelength, if it is going from rarer medium to denser medium, wavelength decreased by n times. That is, what is n? Refractive index, relative refractive index of denser medium. Okay. So we'll explore the properties of wave such as its wavelength and speed are affected during this process. So here we have figure 10.4, which visually represents the refraction of wave as it enters denser medium. So now let's focus on the ratio of wavelengths, lambda 1 over lambda 2. Okay, so this ratio is crucial because it helps us understand how the wavelength changes when the wave enters a denser medium. So this equation lambda 1 over lambda 2 equals BC over AE shows us the relationship between the wavelengths and the distances traveled by the wavefronts. Okay, so this equation highlights how the change in wavelength is directly proportional to change in path lengths of the wavefront. So finally we have the equation lambda 1 over lambda 2 equals to V1 tau over V2 tau. Okay, which is equal to V1 upon V2, where V1 and V2 are the wave speeds in respective media. This tells us that change in wavelength is also related to change in wave speed. As the wave enters a denser medium, its speed decreases, leading to shorter wavelength. So wavelength also decreases. Okay, so this is a fundamental concept in understanding wave behavior during reflection. So when light enters from rarer medium to denser medium, its speed and wavelength both decreases. So here we have the equation lambda 1 upon lambda 2 equals to V1 tau upon V2 tau equal to V1 upon V2. This equation shows the relationship between the wavelengths and velocities of a wave as it moves from one medium to another. So next we see the equation V1 upon lambda 1 equals to V2 upon lambda 2. This tells us that the ratio of velocity to the wavelength remains constant across the boundary. So V upon lambda is constant. Okay, across the boundaries, across two different media. So now let's look at the equation. So what is nu equal to V upon lambda? Okay, so V1 upon lambda 1 will be equal to nu 1. and v2 upon lambda 2 will be nu 2. What is nu? Frequency. So equation becomes nu 1 equals to nu 2, where nu equals to v upon lambda. This indicates that frequency of the wave remains unchanged when it enters a denser medium. The frequency is a fundamental property of wave that does not alter or change with the medium change. So frequency remains same. Both wavelength and speed change with the same factor. Okay, but frequency will not change. Frequency will remain constant. So the equation implies that when a wave enters a denser medium, the speed of the wave decreases as indicated. Okay, so V1 will be greater than V2. V2 is the denser medium. So speed in the first medium will be greater. N21 is greater than 1. So refractive index of second medium will be greater. That's why speed will be slow in the second medium, but frequency remains same. So finally, we see that both wavelength lambda 2 equals to lambda 1 upon n21 and speed v2 equals to v1 upon n21 decreases in a denser medium while the frequency remains same. This is key takeaway. The medium affects speed and medium but not frequency. Understanding this help us predict wave behavior in different materials. So we are going to explore how light refracts when it moves from one medium to another, specifically from denser to a rarer medium. Okay, we have discussed when light goes from rarer to denser medium. Now we are going to discuss when light goes from denser to rarer medium. Our objective is to find the refracted wave using Huygens principle. Notice the image here, which shows the plane wave bending away from the normal as it enters a rarer medium where the speed of light is greater. So figure 10.5, refraction of a plane wave incident on a rarer medium for which V2 greater than V1. The plane wave bends away from the normal. Okay, so as you can see in the diagram, light or wavefront is going from denser, that is medium 1. Now medium 1 is denser, so it is going from denser medium to rarer medium, that is medium 2. So speed of light in rarer medium is more, that is V2 is greater than V1, and that wavefront is incident on the interface at angle I, that is angle of incidence. Okay, so consider the scenario where a plane wave is refracting at boundary of a rarer medium. Here the refractive index of the first medium n1 is greater than that of second medium n2, and the speed of light in the first medium v1 is less than in the second medium. Okay, that is v2. So v1 is less than the v2. So to determine how the wave bends when it enters the second medium, we need to follow the systematic approach. We will start by identifying the specific point at the interface where the wave enters the new medium. So let's pick a point labeled as point A at the interface between the two media as shown in figure 10.5. This point will serve as our reference for drawing the wavefronts and understanding the refraction process. So from point A, we draw a sphere with the radius equals to v2 times tau. Okay, where tau is the time elapsed. This sphere represents the wavefront in the second medium, expanding outward from point A. Next, we draw the tangent plane labeled as CE from point C on the sphere. This tangent plane is crucial because it represents the new wavefront in the second medium. By drawing this tangent, we can see how the wavefront changes direction as it enters the rarer medium. Okay, so finally we note that the segment AE equals to V2 times tau, where tau is the time taken for the wave to travel from A to E. The line CE represents the refracted wavefront. Okay, this visualization helps us understand how the wavefront bends away from the normal, confirming the principles of refraction in a rarer medium. So today we are going to derive Snell's law, which explains how light bends when it passes from one medium to another. Our focus will be on diffraction at a rarer medium where the speed of light increases. So let's examine the triangles in the diagram. In triangle ABC, we can relate the angle of incidence to the sides of triangle. So now observe how we express the sign of angle of incidence. We have sine I equals to BC upon AC, which is equal to V1 tau upon AC, where V1 is the speed of light in first medium and tau represents the speed time taken for the wave to travel. Similarly, in triangle AEC, we express the sign of angle of refraction R. We have sin R equals to AE upon AC, which can be written as V2 multiplied by tau upon AC. In this case, V2 is the speed of light in the second medium. So let's start by considering two equations that describe the situation. This equation will help us understand the relationship between the angles and incidence, angles of incidence and refraction. So sin I equal to BC upon AC, which is equal to V1 tau upon AC. Sin R equal to AE upon AC, which is equal to V2 tau upon AC. So let's divide these two equations. So sin I upon sin R is equal to V1 tau upon AC over V2 tau upon AC. Okay, so this simplifies to sin I upon sin R equals to V1 upon V2 in the next step. Okay, so tau and tau will get cancelled out. Also AC and AC will get cancelled out. Okay, so sin I upon sin R equal to V1 upon V2. This is Snell's law, which shows that ratio of sign of angle of incidence and diffraction is equal to ratio of velocities of light in the two media. This fundamental law helps us predict how light will bend when it enters the different medium. So now let's define the refractive index for two different media. For the first medium, we have N1 equals to C upon V1. And for the second medium, N2 equals to C upon V2. Here C is the speed of light in vacuum and V1 and V2 are the speed of light in the respective media. Now we will divide these two expressions. By dividing, we get N2 upon N1 equals to V1 upon V2. This equation shows the relationship between the refractive indices and the speed of light in the two media. Notice how the ratio of refractive indices is inverse of the ratio of the speeds. Now let's introduce the concept of angle of incidence and refraction. We use the equation sin I upon sin R equals to V1 upon V2, where I is the angle of incidence and R is the angle of refraction. So by substituting the previous relationship, we find that sin I upon sin R equals to N2 upon N1. This is a key step in deriving Snell's law, as it links the angle of incidence and refraction to the refractive indices. So this leads us to equation N1 multiplied by sin I equals to N2 multiplied sin R. This is the mathematical expression of Snell's law. It tells us how the angles of incidence and refraction are related through the refractive indices of two media. So we have derived N1 multiplied by sin I equals to N2 multiplied by sin R, which is known as Snell's law. This law is fundamental in understanding how light behaves when it passes through different media. So our objective here is to understand the concept of the critical angle denoted as IC. This is an important concept in optics, particularly when discussing how light behaves at the boundary between two different media. So here we have figure 9.11, which visually represents the scenario we are discussing. Notice how the light is traveling from one medium to another. This image will help us understand the behavior of light at the boundary. So let's consider the situation where light travels from denser medium to rarer medium with refractive index n1. Okay, to a rarer medium with refractive index of n2. It's crucial to remember that n1 is greater than n2. Okay, in this case. So according to Snell's law, the relationship between the angle of incidence and angle of refraction given by the equation sin I upon sin r equals to n2 upon n1, which implies, or this can be rearranged as sin r upon sin I equals to n1 upon n2. This equation is fundamental in understanding how light bends when it passes between different media. So since n1 is greater than n2, refractive index of first medium, that is denser, is greater than the refractive index of rarer medium. It follows that sin r is greater than sin I. Means the angle of refraction is greater than the angle of incidence I. So as a result, the refracted ray bends away from the normal. This behavior is typically when light moves from denser to rarer medium. If we continue to increase the angle of incidence I, there comes a point where the angle of refraction reaches 90 degrees as shown in the figure also. Okay, this specific angle of incidence is known as critical angle and represented by IC. You can see in the diagram the angle of incidence for which the angle of refraction becomes 90 degree, or refracted ray will go along the interface, is known as critical angle. So understanding this concept is crucial for applications like fiber optics and total internal reflection. So when the angle of refraction R is 90 degrees, the sine of R becomes 1. This means equation sin I equal to n2 upon n1. Sin I upon sin R equal to n2 upon n1. But sin R is 90 degree, sin 90 degree is equal to 1. So sin R becomes equal to 1. So sin I equal to n2 upon n1. So let's introduce the term critical angle. This is a specific angle of incidence at which the refracted angle is exactly 90 degrees. We denote the critical angle as IC. It's important because it helps us, it marks the threshold beyond which light will not pass into the second medium but instead reflect entirely within the first medium. So building on that, for any angle of incidence greater than the critical angle, that is I greater than IC, there will be no refracted wave. This means the light does not pass into the second medium at all. So when the angle of incidence exceeds the critical angle, total internal reflection occurs. This means that instead of refracting, the light is completely reflected back into the original medium. This principle is used in various applications, such as in the design of fiber optic cables, where light is kept within the cable by total internal reflection. So our objective is to derive the law of reflection here, which states that the angle of incidence is equal to angle of refraction, or I equal to R. This foundational concept in physics help us understand how light behaves when it encounters reflective surfaces. So let's start by considering a plane wavefront labeled AB, that is incident on a reflecting surface Mn. Okay, like a mirror or any reflecting surface. The angle of incidence denoted by I is the angle between the incoming wavefront and the normal to the surface. Okay, so you can see reflection of a plane wave AB by reflecting surface Mn. AB and CE represents the incident and reflected wavefronts. Figure 10.6. Okay, so I is the angle between the incoming light ray, incident ray, and normal to the surface, or it is the angle between the incoming wavefront, plane of incoming wavefront, and the plane of surface, reflecting surface. So next we need to consider the speed of light in the medium, which we will denote as V. This speed is crucial because it determines how quickly the wavefront travels through the medium. Keep in mind that speed of light can vary depending on the medium it travels through. Now let's introduce the concept of time denoted as tau. This is the time taken for the wavelet from point B on the wavefront to reach point C on the reflecting surface. At this point, we can express the distance BC as the product of the speed of light and the time taken. Okay, so the time taken by secondary wavelets from B to reach C. Okay, so speed of wavefront or speed of wave in that medium is V, and tau is the time taken to reach secondary wavelet from B to C. So what is the distance of between B and C? So BC equal to speed into time. So speed is V. So V multiplied by tau time. This equation shows us how the distance traveled by the wavelet is directly proportional to both the speed of the light and time it takes to travel. So let's consider how we can predict the direction of wave after it reflects. The first step is to identify point A on the diagram. This is where we will start our construction to find the reflected wavefront. So we draw a circle from point A. Imagine this as a sphere in 3 dimensions. This circle represents the wavefront emanating or emerging from point A, and it will help us visualize the wave's path. The radius of the circle is crucial. It is equal to the distance AE, okay, which is also equal to BC. So by the time secondary wavelet from B reaches C, during same time secondary wavelet from A reaches E. Okay, since incident light and reflected light is in same medium, so speed will remain same, that is V. Okay, so AE distance is also equal to BC, which is represented by the expression V multiplied by tau. Here V is the wave's velocity and tau is the time interval. So now from point C, we draw a line touching the circle at point E. Okay, this line is the tangent to the circle, and it plays the key role in determining the direction of reflected wave. Okay, so we draw a circle by taking BC distance equals to AE, or we can say AE equal to BC. We draw a circle, and now from point C, we draw a tangent to that circle. So that CE represents the reflected wavefront. So finally, the surface CE, which is tangent to the surface, represents the reflected wavefront. This is the new direction the wavefront will take after reflection. So let's define our terms. The angle of incidence I is the angle between the incoming wavefront and normal to the surface. Similarly, the angle of reflection R is the angle between the reflected wavefront and the normal. Let's consider two triangles in our diagram, triangle EAC and triangle BAC. These triangles will help us understand the relationship between the angles of incidence and reflection. In both triangles, the distance AE equals to BC equals to V tau, where V is the velocity of the wave and tau is the time. This is because both distances represent how far the wavefront travel in the same amount of time. Okay, so distance traveled in the same time tau. Since reflected wavefront and incident wavefront is in same medium, so velocity will be V and tau is the time taken. Okay, so that's why AE distance is equal to BC distance. Okay, so this equality is key to establishing congruence between the triangles. So now AC is common side to both the triangles EAC and BAC. This shared side is another important factor in proving the congruency of these triangles. Okay. So two sides are same. Okay. And also one angle AEC equal to ABC. That is 90-degree angle. Okay. So this is because the wavefront is always perpendicular to the direction of propagation. Okay. So direction of propagation is towards A, shown by arrow. Also, direction of propagation is from B to C. Okay, so it is perpendicular to the wavefront AB. Also, direction of propagation of wavefront AE, of reflected wavefront AE, is perpendicular to reflected wavefront CE. That's why angle AEC and ABC are 90-degree. A wavefront is always perpendicular to the direction of propagation. This perpendicularity is a fundamental property of wavefronts and it's essential for congruency proof. Okay, so by RHS congruency, delta EAS, sorry, triangle EAC is congruent to triangle BAC. So by the RHS right angle hypotenuse side congruency criterion, we can conclude that triangle EAC is congruent to triangle BAC. This congruency implies that angle of incidence I equals to angle of reflection R. Okay, thus proving the law of reflection. So this is the congruency between the triangles. So we have two congruent triangles, delta EAC and delta BAC. Because these triangles are congruent, the corresponding angles and sides are equal. Okay, so this means the angle BAC is equal to angle ECA. Okay, so let's identify these angles in the context of reflection. From diagram, angle BAC is the angle of incidence denoted as I, and angle ECA is the angle of reflection denoted as R. This connection between the angles and their respective roles in the reflection is key to our derivation. Okay, so finally we conclude that since angle BAC equals to ECA, it follows that I equals to R. This is the law of reflection. The law states that the angle of incidence is equal to angle of reflection. Okay, so how angle BAC is I? Because angle of incidence, the angle between the normal and incident ray is I. Okay, so by geometry we can find angle BAC is also I. Okay. Now we are going to explore the behavior of prisms using wave theory. Our objective is to understand how light behaves when it passes through a prism. Okay, so let's take a look at figure 10.7a, which shows the refraction of a plane wave by thin prism. Notice how the wavefront interacts with the prism. So in this figure, we see the plane wavefront passing through thin prism. It's important to note that wavefront is initially straight before it encounters the prism. As the straight wavefront hits the prism, the bottom portion of the wavefront passes through the thicker part of the prism. This is a key point because the thickness of prism affects the speed of wavefront. Since light travels slower in the glass than in the air, the bottom portion of the wavefront slows down and gets delayed. This delay is crucial because it leads to change in the wavefront's orientation. Okay, so upper part, for the same time, upper portion of the wavefront travels more distance than the lower portion. So as a result of this delay, the wavefront emerges from the prism tilted. This tilting effect is direct consequence of the wavefront's interaction with the prism. Okay, illustrating the principle of refraction and the wave optics. Since light rays are perpendicular to wavefront, if we draw the light rays of perpendicular to this tilted wavefront, it will show the dispersion through the prism phenomenon. Let's take a look at figure 10.7b, which illustrates the refraction of a plane wave by convex lens. Notice how the wavefront approaches the lens. This image will help us visualize the change that occurs as light passes through the prism. So in this figure, we see a plane wavefront incident on a thin convex lens. Pay attention to the structure of lens as it plays a significant role in the refraction process. So notice that the middle part of the lens is thicker than the edges. This thickness variation is important because it affects how light travels through the lens. The thicker center will slow down the light more than the thinner edges. Okay, so plane wavefront, the middle portion of the plane wavefront will travel less distance as it gets slowed. Okay, because it is passing through thicker part of the lens. It gets delayed, and for the same time it travels somewhat less distance than the edge portions of the plane wavefront. Okay, so as the light passes through the lens, the middle portion of the plane wavefront slows down more due to increased thickness. This slowing down is a key factor in how the wavefront changes shape as it exits the lens. Conversely, the edge parts of wavefront slows down less because they pass through the thinner parts of the lens. This difference in speed across the wavefront is what causes the wavefront to change its shape. The result of these differences in speed is that the emerging wavefront becomes curved, taking on a ball shape. Okay, so this curvature is essential for focusing light as it directs the light towards a specific point. Okay, so when we draw light rays perpendicular to this refracted wavefront, these light rays converge to one point, that is focus. Okay, so emerged wavefront converges to a point known as focus, labeled as F. This is where the light rays meet after passing through lens, demonstrating the lens ability to focus light. So in figure 10.7c, we see a plane wavefront incident on a concave mirror. This is the initial interaction where the wavefront meets the mirror surface. It's important to note how the shape of the mirror will influence the path of light waves. So after the wavefront reflects off the concave mirror, it transforms into a spherical wavefront. This spherical wavefront converges towards the focal point labeled as F. This convergence is a key characteristic of concave mirrors which focus light to a specific point. Notice how the reflected light wavefront converges to a single point known as the focus. This is similar to how a magnifying glass can focus sunlight to a point, creating intense heat. So this focusing effect is like how a satellite dish collects signals at one point. Just as the dish gathers signal from a broad area and directs them to a receiver, the concave mirror collects light and focuses it to a point. So summary, Huygens principle and its application. Okay, Snell's law is a fundamental principle and Huygens law can be used to derive Snell's law. Okay, so Snell's law is a fundamental principle in optics that describe how light bends when it passes from one medium to another. The equation n1 sin I equal to n2 sin r shows the relationship between the angles of incidence and refraction, where n1 and n2 are the refractive indices of two media. Okay, so the equation sin I upon sin r equals to v1 upon v2 equals to n2 upon n1 connects the angle of incidence and refraction with the velocities of light in two media. This tells us that the ratio of the sines of angles is equal to the ratios of the velocities, which is also equal to the inverse ratio of the refractive indices. In a denser media where n2 is greater than n1, the wave bent towards the normal. This this happens because the velocity of light v2 is less than v1 in the denser medium. Conversely, in a rarer medium where n2 is less than n1, the wave bends away from the normal. Here the velocity of light v2 is greater than v1, causing the wave to bend away. This is important for understanding how light behaves when it moves into a less dense medium. An important point to remember is that the frequency of light remains constant during refraction. However, both the velocity v and wavelength lambda change. This is expressed in the equation v equals to nu lambda, where nu is the frequency. Let's shift our focus to reflection. In reflection, the angle of incidence equals to angle of reflection, denoted as I equals to R. This principle is fundamental in understanding how light reflects off surfaces, maintaining the angle relationship between the incident and reflected rays. Wavefronts are always perpendicular to the direction of wave propagation. This perpendicular relationship helps us visualize how waves move through different media and is essential for understanding wave behavior in different contexts. Here we have a light ray traveling from water to air. The refractive indices are given n1 equals to 1.33 for water and n2 equals to 1 for air. The angle of incidence is 30 degree. Okay, so calculate the sin R using the Snell's law. Okay, so let's consider the speed of light in these media. In medium 1, the speed of light 2 multiplied 10 is per 8 meter per second, and in medium 2 it's 1.5 multiplied 10 is per 8 meter per second. Okay, so we can find the ratio of the refractive indices n2 upon n1. So next, for a plane wave, the angle of incidence is 45 degrees. What will be the angle of reflection? Next question, light traveling from glass to water. Here n1 equals to 1.5 for glass and n2 is 1.33 for water, with an angle of incidence 30 degrees. Okay, so again we will use Snell's law and calculate sin R. Finally, if a light wave has a wavelength of 500 nanometer and enters a medium with a refractive index 1.5, what will be its new wavelength? So this is all about today's lecture. I hope you enjoyed the session and understood it well. Thank you.